Now we have all the tools required to move on and to start describing. Now we have all the tools required to move on and to try to prove Carnot efficiency. Okay, so now we'll be working on Carnot efficiency or Carnot cycle efficiency. To do this, we will use 3 different reversible cycles. Okay, so let's start with a reservoir always at temperature TH. Okay, and we'll connect to this reservoir a reversible heat engine. We'll be calling A. This one is reversible, is getting certain heat QA, and it's rejecting heat that will be calling QB. Okay, and this heat engine is providing us with a certain work called WA. And then we'll be connecting a second one to this one. We'll call it B, and it's also reversible. And it's getting heat from QB, and obviously it has to reject a certain heat, otherwise it will be violating the second law of thermodynamics. And we'll be calling this rejected heat QC. And all this is connected to a reservoir at the temperature TL. Now we'll do the same thing also, but with one reversible cycle. So here we have, instead of having 2, we have C, which is also reversible, getting heat QA from the reservoir TH and rejecting QC into the reservoir TL. And this will provide us with the work, which is WC, and B will provide us with the work we'll be calling WB. So to summarize, we have 2 heat engines here, reversible heat engine A and B, and we have here another one which is massive, and it's called C, which is also reversible. Okay, the important thing here to see is that A and B are connected between TH and TL, and the same case for C. Okay, so here what do we know? We know that, well, the work C, okay, has to be equal to the sum of the 2. So the work C is equal work A plus work B. And we know also something important, which is that the thermal efficiency of A and B has to be equal to the thermal efficiency of C. So the thermal efficiency of A and B must be equal to the thermal efficiency of C. This is following Carnot principle, since we said that as long as you give me 2 temperature reservoirs, here they are set as TL and TH, whatever I do in terms of heat engines or whatever I put in between, if I'm claiming that they are reversible, so they have to have the same thermal efficiency. Here what I'm putting is A and B, this, and here I'm putting only one, which is C. So Carnot principle is telling us that they have to have the same thermal efficiency. Now let's try to write the thermal efficiency of A. The thermal efficiency of A is equal to what? It's equal to the work A over the heat we are inputting, which is QA. But it's also equal to 1 minus Q out, which is QB, over QA. and this is equal to, Carnot principle is telling us that the most important thing, since they are reversible, is the temperature difference, okay? This means that what determines the efficiency of a reversible heat engine is only the difference in temperature. So we can write that this is a function of TA and TB, okay? Or we can write, if we want, that this ratio QB over QA is equal to another function, which will be equal in this case to 1 minus this function, TA TB, right? We'll be doing the same thing then for B and for C. So the thermal efficiency of the heat engine B is equal to the work B over the heat input here, which is QB, and it's equal to 1 minus, we are rejecting QC here, and our input is QB. So QC over QB, and it's also a function of now the temperatures TB and TC. And this ratio, which is QC over QB, we can write it as a certain function f, capital F, of TB TC. And the last one, our thermal efficiency for heat engine C is equal to what? Engine C is producing a work WC and has QA as an input in terms of heat. So this is WC over QA, which is equal to 1 minus its QC, this is what we are rejecting, our Q out, over QA. And this is equal to a function of, in this case, TC and TA, or TA, TC, or this ratio here, QC over QA, is equal to a certain function, capital F, of TA, TC. So far we have demonstrated that the ratio QB over QA is equal to a certain function of only the temperatures TA, TB. The same way QC over QA, or QB, sorry, is equal to a certain function of TB, TC. And finally, QC over QA is equal to a certain function of TA, TC. Remember, this is valid for reversible heat engines. But we can always write that QC over QA is equal to QC over QB cross QB over QA. This implies that now if we replace with different functions, that function of TATC should be equal to the function of TBTC cross the function of TBTA, or TATB. This will put constraints on the way we define this function f, in the sense that this function f has to be constructed in such a way that we'll be canceling the dependence on TB, because you see this is only a function of TA and TC, but here we have a function of TB. So basically we have to construct or select a function f in such a way that TB or the dependence on TB will disappear. We can select different functions. For example, you see that if we select something like TATC, let's say is equal to a certain function phi of TA plus phi of TC. Well, this one doesn't work, right? Because then I would be replacing here phi TA plus phi TC, then cross phi TA plus phi TB, and therefore TB won't, the dependence phi TB won't cancel out. However, so this one doesn't work. However, if I define a function like phi TATC is equal phi of TA over phi of TC. So now this works, all right? Because then I will be multiplying. This one will become phi of TC over phi of TB, and this one will become phi of TB over phi of TA. I can cancel phi of TB, and therefore we'll end up with phi of TC over phi of TA, okay? So this means that this one here will become phi of TC over phi of TA, which is equal to what? This one is phi of TC over phi of TB cross phi of TB over phi of TA. And now it makes sense. Now we have to select this function phi of t, and the simplest one obviously, and this is what Kelvin decided to pick, is that phi of t is equal simply to T, the temperature. You can pick other functions that will fulfill this condition, okay? But this one is probably the simplest one and the more natural one. So, because if you apply this, this will give you that here, TC over TA, so this one, TC over TA, will be equal to TC over TB cross TB over TA, so it makes sense, okay? So now that we did this, this means that the ratio of QC over QA, okay, so the consequence of this is that any ratio of heat, so QC over QA, is simply equal to TC over TA. The same way, QC over QB is equal to TC over TB. And finally, QB over QA is equal to TB over TA. Is this valid for any cycle? No, because you remember that here we claim that we have reversible cycles. Now, this will lead us to a very interesting conclusion, okay? This conclusion is that now the thermal efficiency, for example, of C, which is 1 minus QC over QA, will be rapidly replaced by QC over QA by TC over TA, okay? But here QC is dependent on TH, QA is dependent on TH, and QC is dependent on TL. So we'll see that this will lead us to a very nice compact form, okay? Now, finally, if we consider two reservoirs, TH and TL, and between the two reservoirs we construct a reversible heat engine with, let's say, getting QH from the high temperature reservoir and rejecting a certain QL and providing us with work which is reversible. Now we know that we can write that the thermal efficiency of this cycle, heat engine, is equal to work net over Qn, which is QH here. Following the first law of thermodynamics, we know that the work net is equal to QH minus QL, and this will lead us to 1 minus QL over QH. Okay? So we used to stop here, okay? But now, what do we know? We know that this is a reversible heat engine. So, but this is a reversible heat engine. And we have shown that if I have a reversible heat engine, the ratio of the heat is equal to the ratio of temperatures. So QL over QH is equal to what? Is equal to TL over TH. Which is cool here because now I can replace QL over QH here by this term. And this will give me the following expression for the thermal efficiency: 1 minus TL over TH. Okay? And we'll be calling this Carnot efficiency for a heat engine running between TL and TH. And this will represent the maximal thermal efficiency we can get for this heat engine, but also for any reversible heat engine and for any heat engine running between TL and TH. And obviously, this one is still lower than 100%, okay? Otherwise, if it's equal to 100%, it will be violating the second law of thermodynamics. What does it mean? This means that as soon as you set the temperatures TL and TH, the maximum you can get from this heat engine is defined by 1 minus TL and TH, okay? So, for example, let's say if we pick TH as, let's say, 3000 Kelvin, TL, let's put it at 400 Kelvin. So this means that any heat engine I will be designing between 3000 Kelvin and 400 Kelvin cannot have a thermal efficiency which is higher than 1 minus 400 over 3000, okay?